In this recording, we're going to look at something called Newton's law of cooling. And basically, as it says here in the intro paragraph, it's a great example of a transformed exponential function. We've studied several exponential functions in this unit, and here we're going to apply one of them. So let's consider this decreasing exponential function. And I guess first off, how do you know it's going to be decreasing? So consider that for a second. Hopefully you recognize because the base is between 0 and 1, we're going to be multiplying by half each time. It's going to make the overall amount smaller as x increases. So exercise A says make a sketch from your calculator. So if you have a calculator, go ahead and put this in your y equals. Set up your window to match the dimensions here. Play your recording after you've made your sketch. Okay, so hopefully you took time to make that sketch. And as we can see here, the curve decreases from 8 and down. I'm just going to do a little screenshot of that. And it says clearly the value of y gets smaller as x gets larger. Does it ever reach 0? So consider that for a moment, and then play the recording when you're done. Okay, so one way to think about this is you're getting half of the previous value each time. So we take half of 8, then half of 4, then half of 2, half of 1, etc. Keep getting half. Are you ever going to reach 0? It doesn't make sense. You would never get 0. Only way we would get 0 is if we're multiplying by 0. Okay. So let's apply this idea. We're familiar with this graph. Now let's apply it to a temperature of a liquid cooling in a large room. So something pretty common. You warm up a cup of water. Maybe you're going to make some tea, hot chocolate, coffee. Put it in a room that has a steady temperature of 70 degrees. Pretty common room temperature. And let's assume that the liquid starts at 200 degrees. Keep in mind, boiling is 212, so this is just below boiling water. And let's draw what we think the rough sketch might be and put some numbers on here. Put some numbers on the x and the y axes and play the recording when you've got a sketch what you think it will look like as time increases. Okay, so hopefully you made this sketch. At this point, this is going to be temperature in degrees Fahrenheit. This is time measured in minutes. All right, I hope you recognize that the temperature starts out at 200 degrees. So I'm going to start this axis at 200. Label where 100 would be. All right. And I know it's not going to get cooler than the room, right? The room's not going to make the liquid get cooler than 70 degrees. So I'm going to get close to 70. So I'm going to mark where I think 70 is about here or so. And that's where I think it's going to get after a particular amount of time. Well, let's say 2 hours. So 120 minutes. Maybe it'll get pretty close to that. I'm going to draw out here what's called a horizontal asymptote, which is the temperature that it's going to get close to. And then I'm just going to draw a curve. Something like that. It's going to go down and get close. Right? Maybe it's even going to be steeper initially, cooling off quicker, and then flattening out. All right, so based on this, why would this not be a good model? So consider that and play the recording when you're ready. Hopefully you took time to consider that. If not, you should do so now. This doesn't really make sense because what we have here has a horizontal asymptote at y equals 0, right? So there needs to be some shifting up of this graph to the horizontal asymptote of 7. Okay? So we're going to have a c value that represents the shift up of a particular number of units. All right, so at this point, let's apply this. We've got the same idea. We're going to stick with a 200 degree starting temperature and a room that is 70 degrees. And we're going to use the same model that we developed. There's a little typo over here. This over here should be an F. Make that an F right here. Because our initial function is called ft. Alrighty, so which of these constants is equal to 70 and why? Again, I'm asking you to pause and consider this. Hopefully you considered that and thought that 70 should be the shift up. Okay, so we know what C is. That's the amount it shifts up. That's the temperature it's not going to go below. It's not going to get cool in the room, right? It just doesn't make sense. None of these constants is equal to 200, but when we start out at time 0, we have a temperature of 200. So this lets us figure some stuff out. So let's figure that out. Why don't you play the recording when you're ready? Okay, so hopefully you took time to do that. F of 0 is 200, so we're going to say 200, that's what F of 0 is, equals A, which we don't really know what it is, times B, which we don't know what that is either, to the 0 power. We do know when time is 0, that's the exponent, and we happen to know what C was, right? 70, we just found that out over here. So we can solve this, because B to the 0, that's just a 1, right? So we have A times 1 plus 70. Well, the only number that makes sense there is 130, right? 130 plus 70. All right, so I've got a C value and an A value. Now we should be able to find out a B value. What information would we need? Well, if we knew A and C, we wanted to find B, we'd have to know like an X and Y pair, a temperature and a time pair. Okay, so they're going to give us that. So they're saying, all right, after 5 minutes, it's all the way down to 153. So this thing is cooling rapidly. Let's now go ahead and find out what B is. Okay, so we know lots of these pieces. So we know the temperature, 153, of the liquid is equal to A, we already know is 130. B is unknown, but we know it's being raised to the 5th power because every minute we decrease the temperature, and 5 represents time. And then we have our C value. I'm just substituting in all the knowns into this function. Now we just find out what B is. So we're going to subtract 70 on both sides. It gives me 83 on the left. And I'm going to divide by 130. So when I divide by 130, I get, and in the interest of space, I'm not going to show that division, but hopefully that makes sense to you. And that's going to be equal to B to the 5th power. How can we get rid of a 5th power? Well, hopefully you've thought about that. We talked about that in class. You're going to undo it by doing a 5th root, right? So you can square root, you can cube root, you can root any unwanted exponent. And so you just pop that in your calculator. Let's show what that will look like. I want to model that for you, be as precise as we can. So let's come over here, and back on our home screen, let's do 83 divided by 130, get your value, and then do the 5th root of that. So we're going to hit Math, Choice 5. I've got to bring back my cursor on here and say I want the 5th root. And then I'm just going to cursor up on top of that number. That pastes it in, and that's going to be as precise as I can be. So now I can round it to whatever I want. In this case, the 100th place, 0.91. So now I know what B is. All right, and so the next question says, what is the temperature after half an hour, after 2 hours? So go ahead, now that we have a function, we have this nice function, f of t equals, we know the a value, was 130. We know the b value, we just figured that out, 0.91. T is the variable, the independent variable, and we know our room temperature is 70. So I'd like you to find out each one of those. I'd like you to use your calculator to make a sketch of the graph, and then the final part we can work on together. Play the recording when you're ready. Okay, so hopefully you took time to do that. Hopefully you were careful here that t is measured in minutes. Okay, so you've got to go back up to how t was defined. T is time in minutes, and these are given in hours. So if you put in here 1/2, that's not quite right. You should be doing that in terms of 30 minutes. Now let's think about why this is. If you take a number that's less than 1, and you raise it to the 120th power, a big power, you multiply that over and over and over, it's going to start to get pretty small, right? This thing is getting smaller and smaller. You're just taking 10% less and 10% less, or 9%, I guess. It's going to get really small. This thing right here is going to practically be 0, right? After you do it so many times. So that's why we're getting really close to 70. Now in terms of making your graph. That's 200. Here's our asymptote. We know we're going to get really close to 70, and it does drop off pretty quickly. By the time we get to 40 minutes, this was in degrees Fahrenheit, drops off pretty quickly. Okay. And finally, this is the interesting stuff. This is where we get to use our new tools to find unknown time. All right, so I want to know when the thing will be 100. So that's 100 degrees equals, and then we've got our 130 times 0.91 to the unknown t plus 70. So take a moment to work this out. Play the recording when you're ready. Okay, so hopefully you worked this out. You subtracted 70 from both sides. All right, so we got 30 on this side. Can't multiply these, right? I have to do exponent before multiplication, so I want to undo the multiplication. So divide both sides by 130. When I do so, okay, now I'm stuck. Remember, when you're stuck in exponential form, think log form. Okay, so let's show what that looks like on our calculator. I'll be as precise as I can here. So first I'm going to do that division. Then I'm going to do a log with the base of 0.91. That allows me to be as precise as I can. So, to the nearest tenth, 15.5 minutes. Okay, and that seems reasonable because it would get to 100 early on. Okay, it took almost 40 minutes to get right down to 70. All right, thanks for watching.